Okay, so this is the lecture 10 for this course on Introduction to Differential Geometry. So as we recall from our previous session, we had just begun our discussion on the Gaussian mean and principal curvatures. So at first we began with understanding what Gaussian and mean curvatures imply. Right. So the definition for the Gaussian curvature was that at first we would have to Gaussian and mean curvatures was that we started with a Weingarten map of an oriented surface S at any point P which belongs to the surface S. Then we derive the expression for the Gaussian and mean curvatures in terms of some properties of the map itself, right? So K happens to be the determinant of Weingarten map, and H was the half of trace of the Weingarten map. And recall Weingarten map was a linear map, right? So and it mapped from a vector to a vector. So essentially, in matrix representation, of course, I mean, in tensor, what do you call, from a tensorial perspective, it represents a second order tensor, and in metric, in say in its component representation, the components fill up a matrix, right? So essentially, we have the Weingarten map here, right? So this is the Weingarten map. Then we represent it in any basis. So say, then we obtain a matrix from that. Then we determine the determinant and the sum of diagonal entries, which happen to be the trace, right? So recall that the determinant and the sum of trace, I mean, the trace of a matrix is invariant with respect to any coordinate system. So no matter in which coordinate system we would want to represent the tensor in, the properties such as determinant and the trace remains invariant to that, right? Now, Weingarten map, what it does is it gives us the rate of change of the Gauss map, right, with respect to the coordinate lines, so to speak, or with or the derivative of this on the surface, derivative of the Gauss map on the surface, right? So, say if we have a vector which is parallel to sigma u. Sigma u is one such basis. There are two bases, right, which we can obtain by differentiation of the surface patch with respect to the u and v coordinate lines. So w of sigma u is equal to minus nu, and w of sigma v is equal to minus nv, right? And if n changes its sign, then w, of course, will change its sign because it's linearly dependent on it. So this implies that k is invariant to the sign change of n for the very reason that determinant involves some sort of a product between two such derivatives of normal vector, right? Because of which, if it changes its signs, doesn't matter because the product will involve just a product of -1 and -1, right? So essentially, it remains invariant to that. However, h is depends on the sign of n by virtue of its being just the sum of n. So if the sign of n changes, then of course h will also be, if n say becomes minus n, then h will also become minus h, right? Okay, so K is defined for any surface S. So that's the good, good thing about about K is that it is even defined for an orientable or non-orientable surfaces. However, for H, it can be, uh, say, obtained only up to a sign. So that is the this so to speak, one such demerit of H. But anyway. Now we go move on to determining the explicit expressions for K and H. So we started with the surface patch, and we talked about both the first and second fundamental forms, and we also defined the symmetric 2x2 matrices. Later on, we moved on to stated a proposition here stating that we have sigma being a surface patch of an oriented surface, then the matrix corresponding to WP of S, which is the Weingarten map, with respect to the standard basis sigma u sigma v of the tangent plane, is F1 inverse into F2. And then we moved on to give an explicit representation of K and H by following the steps. And then we presented an example where we considered a surface of revolution. And there was some condition on the profile curve stating that uh, it happens to be unit speed curve. So which means that f dot square plus g dot square is equal to 1. Right? Okay. So now we moved on to determining K and H. And eventually we were able to determine K as minus f double dot by f, and H is equal to f dot g double dot minus f dot g dot plus g dot divided by 2f. And for a ruled surface, we concluded that K happens to be for a ruled surface, K is negative, as we can see clearly, or it's 0. And the denominator always stays greater than 1, greater than 0. Okay? So that was the requirement for a ruled surface. And so ruled surfaces can be so things as that um, say axisymmetric cell can be a ruled surface, right? And of course, there are many such ruled surfaces such as cylinder, cone, and ribbons in mechanics, right? So these are the ruled surfaces. Oh, no. So we have tried to derive the expressions for H and K using what we call as the first and second fundamental forms. But Gauss had also discovered a way to obtain the Gaussian curvature from the Gauss map itself, right? So rather than from its derivative, the Weingarten map. Um, so the analogy was that if, say, so there is another approach, right? Another approach to compute Gaussian curvature. So the idea it borrows from is that, say, if so it's an analogy to, say, if gamma vector is a unit speed curve, plane curve, right? Then its sign curvature, so its sign curvature kappa of S is equal to phi dot, and this phi dot was the angle between the tangent vector gamma vector and any fixed direction, any fixed axis, right? Any fixed vector. So implying that right? This implies that the signed curvature is the rate of change of direction of the tangent vector of gamma vector per unit length. So this was the idea in the uh, plane curves approach. So likewise, analogous. Sorry. So following this analogy, in our case, the tangent plane or the direction of the tangent plane so right is in direction to an, of course, an oriented surface, which is always implied as is of course measured, right? So measured by its unit normal. So of the tangent plane, the direction is specified by by its unit normal and vector. So we might expect that so in a sense that the measure a measure of the curvature of sigma of the surface patch sigma denoted the rate of the change of direction of the tangent vector of gamma per unit length. So likewise, in the case of surface, it would be the measure of the curvature of the surface patch. It would be the rate of the change of n vector, which happens to be the unit normal per unit area. So that is how it goes, right? And it's that's how the analogy works here. So say the way we would put is if the values of n vector at points of S, and if they're recorded by the Gauss map, Gauss map G. So if R is a small region on S containing a point P vector, so we should look at this following ratio. So consider the following ratio. ratio of areas, which is, so the area of Gauss map contained in the region are divided by area of the region itself, right? And this one is consider the following ratio when or as the limiting case of the region are uh, sh shrinking to the point P. So in a sense, the area happens to be just shrinking until it just becomes a point and it reduces that point P. Now let's just go on to state a theorem in this regard. So the theorem says that let sigma vector be a mapping from U to R3, and it is a surface patch, of course. And say we have a point U naught, V naught, in terms of is an element of U. And let delta greater than 0. And it be such that the closed disk R delta U comma V is an element of R2 U minus U naught squared plus V minus V naught squared is less or equal to delta squared. And this is with center at U naught V naught and radius R, oh sorry, radius is of course delta here, and it is contained in U. So this region is contained in U. Then the following limit delta tending to 0 and the area n, the area of the Gauss map in the region R parameterized in terms of delta by a area of the surface patch itself in the same region R delta. This leads us to a this leads to a, it gives us the average, or sorry, it gives us the magnitude of the Gaussian curvature K. So let's reread the theorem. It says that let sigma be a mapping from U to R3, and it is a surface patch. And given that we have a point U naught, V naught, we define a circular, we define a closed disk, right? Which with a diameter, with a radius delta, and call it region R delta, right? And with the center being U naught V net and the radius delta, of course. And it is contained in the parametric space U. Then the limiting case of the ratio of area, which is bound by the Gauss map, and divided by the area of the surface patch for that reason R delta. This gives us the magnitude of the. So this gives us the magnitude of the surface of the Gaussian map at that point u0 v0, which is of course mapped to p vector. So the Gaussian map at at the point p vector, right? So the idea is that this is the where k is the Gaussian curvature. Sigma vector at sigma vector u0 v0, right? Now let's just derive a very basic, this is the preliminary proof of this. For details, of course, we need to please refer to that book, Elementary Differential Geometry by Presley. So here, the area font of the Gauss map in this region divided by the area of the surface patch, R delta. This is equal to, as we recall in the previous lecture. So the area is always given as it was some sort of half of the cross product norm integrated over the surface, right? So it's let's look at the area, so here it would be sigma u cross sigma v and integrated over the parametric space del u del. And of course there will be a half here. So likewise, and half here, which cancels out, right? So we just have. So for our Gauss map, the area corresponding of the Gauss map over a certain region here, it would be given by n vector u, which is the derivative of n with respect to u, cross n vector v, then we have du dv. Now let's try to understand, try to derive the expression for nu cross nv. Right. So as we recall, nu was expressed as a. Of course, we had started with, actually it would have been nu cross minus nu, right? Nv. So this was the Weingarten map for sigma u sigma v. So this is equal to a sigma u cross plus b sigma v cross c sigma u plus d sigma v. Okay. Now this is equal to sigma u cross sigma v is 0, then sigma u cross this, okay, and then we have sigma u cross sigma v is, we can write it as a d sigma u cross sigma v plus now b c sigma v cross sigma u, which is minus from the property of the cross product, it will be minus sigma u cross sigma v. And then of course we have a b sigma v cross d sigma v is just 0. So all that we have is ad minus bc sigma u cross sigma v. And recall, this is the determinant of the Weingarten map. And so determinant of Weingarten map was essentially F inverse F2. F inverse of 1 and into F2. Sorry. Okay. So this comes out to be the determinant of F2 divided by determinant of F1 into du cross sorry, it will be sigma u cross sigma v. Now determinant of F2 by determinant of F1, as we recall, that is the Gaussian curvature K, sigma u cross sigma v. Now we put this expression in the above expression. So we have A n r delta divided by A sigma r delta. This equal to integral of absolute value of K, because the norm can just come out. I mean, so it will be a norm of K sigma u cross sigma v, and since K is a scalar, we can just bring it out of the norm, and with of course with a magnitude, with its magnitude. And then we have this one, uh, sigma u cross sigma v. This is of course this is over the reason delta, and the integration with the integration variables being u and v. So likewise, r delta sigma u cross. So now this becomes, right, now only in the limit. So here we would have to say use some ideas from real analysis, which I won't be doing, because of course that would be it would take quite some time right now. So at best, what we can say is that, say in the limit as delta tends to 0, then in that case, what happens is, so this K happens to be a function of uv. Let me write it explicitly here. And then you have so as delta tends to 0, in that case, what happens is that Ku, so limit of delta tending to 0, so Kuv also approaches this, also, so to speak, tends to K u naught v naught. And since u naught v naught is a point, so it means that K u naught of v naught is just some scalar, right? It's a constant scalar. So in this limit, what we can do is we can just bring out K u naught v naught, right? And then integral of r delta. So in this case, r delta is also tending to 0. But since it's a reason, so it's like where r delta is tending to the point P vector, since sigma of vector of u naught v naught is equal to P vector, right? So the reason is just tending to a vector, to the point P vector, sorry. And then you have sigma u cross sigma v du dv divided by, likewise, r delta tending to the point P vector, sigma u cross sigma v du dv. So eventually all we are, so the numerator, this term and this term cancels out. So we are left with just the absolute value of K at u naught v naught. So that's how we have we are able to prove this this theorem, right? And so when we have a plane, right? So if you, so as an example, let's try to understand something here. So an example goes as, look at a plane, right? So for a plane, n vector is constant, right? Since the entire plane has a unit normal which is the same at every point, right? So in this case, uh, Okay, before this, let me make one thing clear here, because we only talked about the magnitude of the Gaussian curvature. So what we see is that the theorem only gave us the absolute value of the Gaussian curvature K, and we could not know the sign of the Gaussian curvature from the expression. So the sign of the Gaussian curvature K, it can be obtained from the Gauss map, right? And this is only possible if we define the signed area of GR, that is the region of the Gauss map, to be plus minus of AN R, right? And where this sign, where the sign of where the sign of this GR is plus or minus or positive or negative according to an positive or negative according to whether n vector u cross n vector v points in the same or opposite direction as n vector. Right? So in the sense that we can reduce this problem to be, I mean, this theorem, and slightly extend it. So what we have is, so K, it is actually the limit, right? Limit of, say, the region R tending to point P vector of the signed area of the region, integral of region of the Gauss map divided by the area of R. Right? So looking at an example of a plane, n vector is constant, right? So this implies that the signed curvature, or the signed area uh, for any reason R, signed area of GR, right? For any reason R, so it has a single it's a single point. And thus has zero area. So implying that a plane therefore has Gaussian curvature 0. everywhere. Otherwise, say if we look at just the magnitude of K, right? So magnitude of kappa is equal to, so some reason R delta, right? Of say NU cross NV du dV divided by the reason R delta sigma U cross sigma V and du dV. So for a plane, sigma U cross sigma du dV, even sigma U sigma V are just constant vectors, right? So it happens that on the top, or for the numerator, what happens is nu vector is zero vector, cross nv is also zero vector. So, and on the bottom, sigma u vector is equal to say some, if there is sigma u vector is a constant vector, let's call it p vector. Let's call it say r vector, and let's call sigma v is as vector. These are just constant vectors. So we can take this out, right? And then just integrate our r delta over reason. And these are also limiting delta tends to 0. So this one was just du dv. Now, what we see numerator 0 cross 0 is 0. Eventually, we have magnitude of, if the magnitude of Gaussian curvature is 0 everywhere, then of course Gaussian curvature itself is 0 everywhere, right? So this was the idea here. Let's look at another example. It says that show that the Gaussian and mean curvatures of the surface z is equal to f of xy, where f is a smooth curve, is a smooth surface, but in this case, smooth function. To show that k is equal to f of sigma x xx fyy minus fxy0, fxy squared divided by 1 plus fx squared plus fy squared, and then h is equal to 1 plus fy squared into fxx f double f minus 2fx fy fxy plus 1 plus fx squared fyy divided by 2 into 1 plus fx squared plus fy squared 3 by 2. So given that the surface paths, so now let's try to show it. The surface path sigma vector, the surface paths sigma vector of surface S is, say, you can parameter be sigma y is equal to y and z, right? So essentially it is x, y, and f of x. So here x is acting as u and y is acting as v. Right? So let's start with let's determine the first and second fundamental forms. Essentially, that's what we're looking at here. So sigma x vector is equal to 1, 0. And 0 is because x and y are independent coordinates. So the derivative of independent with respect to independent is 0. And then we have fx, right? Partial. Likewise, this one is 0, 1, fy. Using this two, we can construct a normal vector as sigma x cross sigma y divided by the norm of sigma x cross sigma y. And sigma x, this is equal to we'll have a um, minus fx, comma, so minus fy, comma, right, minus fy, comma, 1, right? Divide by root over 1 plus fxy, because the norm is, I'm just taking 1 as the first term in the square root expression. So now let's go on to determining sigma xx. So sigma xx is 0, comma 0, comma fxx. And sigma xy is equal to 0, comma 0, fxy. Likewise, sigma yy is equal to 0, comma 0, then fy. Right? And so we have all the necessary ingredients to determine the coefficients of the first and second fundamental form. So the coefficients for the first fundamental form is E is equal to sigma x cross sigma x, sigma dot sigma x is equal to just 1 plus 1 square plus fx squared, right? And for f, it is, make some space here so that we can compute here itself all the terms. Okay, so for f, it is sigma u, sorry, sigma x vector dot sigma y. And so this gives us fx, fy. And finally, we have g is equal to sigma y dot sigma y. And this comes out to be 1 square plus y square, right? Now let's look at ml. So for the second fundamental form, the first coefficient L is equal to sigma xx dot n vector. So only the third term will count here. So it is fxx divided by root over 1 plus fx squared plus fy squared. Likewise, m is equal to sigma xy dot n vector. And so sigma xy is again just the third component. So it multiplies to this to have fxy divided by root over 1 plus fx squared. And then finally we have n is equal to sigma yy dot n. Right? So this is equal to, again, the third component. So we have fyy divided by 1 plus fx squared Yes. Okay. So we have been able to obtain all the coefficients necessary to determine the expressions for the first. And determine the coefficient for first and second fundamental forms. So all that we need to do now is we'll have to. So K. So that so it's the Gaussian curvature and S are obtained as. So K is equal to L n minus m squared divided by EF EG. That is Ln, yeah, Ln, and then EG minus F. Sorry. Now L is so we can have Fxx into Fyy minus Fxy squared divided by 1 plus Fx squared plus Fy squared divided by EG is E is 1 plus Fx squared and G is 1 plus Fy squared minus of Fx squared Fy squared. So now, so the denominator here goes as, let's only look at the denominator. So denominator is 1 plus Fx squared plus Fy squared plus Fx squared Fy squared minus then Fx squared Fy squared. So this cancels out. So 1 plus Fx squared plus Fy squared. So therefore, K is equal to Fxx Fyy minus Fxy whole square divided by 1 plus Fx squared plus Fy squared whole square. So this was our Gaussian curvature. And for the mean curvature, the expression is H is equal to Lg minus 2mf plus Ne by, this is of course half of this, Eg minus F squared. And I'm sure following the similar steps, we can clearly obtain expression for H, right? So let's now move on to understanding what the principal curvatures of a surface are. In this, before we had just discussed about Gaussian and mean curvatures. So now we talk about principal curvatures. And due to the shortage of time today, we would also need to do at least a lecture on mechanics. So I'll just be talking only about the important things. Like I won't be going very much into like surfaces of mean, constant curvatures and all, right? So after once we are done with principal curvatures, we will directly move on to discussing about the Gaussian theorem aggregate, and that's will just close differential geometry with the with that, and then we'll have a separate lecture just on mechanics of reds, and if possible a bit on ribbons, right? Okay. So now the idea is I will talk about the principal curvatures. of a surface. Right? So what we had learned, one crucial thing that we learned is that the Gauss-Weingarten map is the Weingarten map is self-adjoint. So, okay, so let's start our discussion on this topic with a proposition. So the proposition states as, yeah. So let P vector be a point on of a surface S. And then there are scalars kappa 1, kappa 2, and a basis T1 vector, comma T2 vector of the tangent plane. TPS such that W of T1 vector is equal to kappa 1 T1 vector and W of T2 vector is equal to kappa 2 T2 vector. So it means that if we have for a basis T1, T2 of the tangent plane, there will have this Weingarten map acting on T1 to give us just a scalar multiple of T1, right? So that scalar multiplier, which is kappa 1 and kappa 2, they happen to be the eigenvalue, so to speak, of W of the linear, of the Weingarten map. So moreover, if kappa 1 isn't equal to kappa 2, then T1, T2 is equal to 0. Okay, so here the real numbers kappa 1 and kappa 2 are the eigenvalues of W and T1 vector and T2 vector are the corresponding eigenvectors. That is how it appears in linear algebra, isn't it? So we here specifically we call them that kappa 1 and kappa 2 are called principal curvatures. Right? And principal curvatures of S of the surface S at point P and T1 vectors, T1 vector and T2 vector are called principal vectors. The principal vectors and principal curvatures. Corresponding to kappa 1 and kappa 2. Right now, let's have some few very important notations here. I mean, important terms. Which now say the points of the surface at which the two principal curvatures right? So with the two principal curvatures are equal. Two kappa, say, are called umbilics, right? So there is a term here, and at an umbilic, the equations. So the WT1 vector is equal to kappa 1 T1 vector, and W22 vector is equal to kappa 2 T2 vector. Sorry. Imply that W, that the Weingarten map, acting on any T vector is equal to kappa T vector if T vector is a linear combination of T1 vector and T2 vector. Right? So thus T vector is an umbilic if and only if W Weingarten map at P vector on the surface S is a multiple, is a scalar multiple of the identity map right? And every tangent vector is principal. Is a principal vector, but to the principal direction. Now, say we have a different case here. So if point P is an element of S, is not an umbilic, so it tells us that the principal vectors corresponding to the, so we can just call it principal vector again. Corresponding to the principal curvatures are necessarily orthogonal, right? So in a sense that even if P is an umbilic or not, we can always find two orthogonal principal vectors in TPS, right? And so then we arrive at a corollary here. So corollary states that if a point P, if P is a point, or if simply stated P is an element of S, then there is an orthonormal basis of the tangent plane dp of S consisting of principal vectors. Now, simply speaking, what we have is that the principal curvatures are related to the mean and Gaussian curvatures as follows. H is equal to half of kappa 1 plus kappa 2, and K is equal to kappa 1 kappa 2. So in a sense that uh, essentially it follows from the this can be categorized as a proposition here. Kappa 1, kappa 2, right? Fine. Okay. So the proof of this goes as, so the determinant, right? So the determinant, so the determinant, first of all, W has to be so say in the basis T1 comma T2, which is the principal vectors, the matrix representation of the Weingarten map W is simply, right? So W in terms of T1, T2 basis is equal to kappa 1 okay. So here's kappa 1, 0, and 2. So this is the matrix representation in terms of the uh, principal basis, right? So of course, then it's very clear, right, that the mean curvature, the Gaussian curvature is determinant of W in this basis T1, T2, and this comes out to be simply product, right, kappa 1, kappa 2. Likewise, H is equal to half of trace of W in this basis, so it comes out to be half of kappa 1 plus 2. So that's how it is, right? Now say, in general, how do we determine the principal curvatures, right? So let's just do something here. Let's try to devise an approach. So to compute the principal curvatures, we work in a surface paths, right? And let E du squared plus 2F du dv plus dv squared and L du squared plus 2M du dv plus n dv squared. Let this be the first and second fundamental forms. Right? Right? So as we recall that the Weingarten map, right? The matrix represents how Weingarten map was in terms of, or maybe I'll just clearly state this, the representation of the Weingarten map in the basis sigma u comma sigma v is W is equal to so W is equal to F1 inverse and F2. These are they contain the coefficients of the first and second fundamental forms, right? So the principal curvatures essentially are the roots of the following. Or I should better say that the principal curvatures and principal vectors are the eigenvectors, eigenvalues, and eigenvectors to the following eigenvalue problem. The problem goes as Weingarten map matrix, right? So it will be, say, W minus kappa I identity matrix, this into some T vector is equal to 0, right? So this would effectively be F1 inverse F2 minus kappa I vector, I matrix T vector is equal to. So eigenvalues the roots to the following equation. Right? So then this equation is like determinant of F1 inverse F2 minus kappa I is equal to 0. Right? So, and even this T vector, right? It had to be expressed T vector is like in terms of, but in the basis represented in the basis sigma use. Okay. Right. So this is what we can do here. is equal to 0. And then we can also use that special property, right, of say the determinant. So say F1 inverse we take as the so the factor, we factor out, and then we have F2 minus kappa. And so this, for this to happen, it has to be multiplied by F1, right? So because F1 inverse into F1 gives us identity matrix is equal to 0. And then we further do that, all that. So this comes out to be F1 in inverse. The determinant of inverse is the inverse of determinant. Or maybe I'll just, without complicating it further, and then we'll have determinant of F2 minus KF1 is equal to 0. So this should not be 0. It must not be 0, otherwise it implies that we are unable to. So the length of any segment is 0, which is not true, right? Any segment on the curve, right? So this implies that determinant of F2 minus KF1 is equal to 0. And then this leads us to the following proposition. Proposition goes as the principal curvatures the roots to the following equation. Roots of the, then it's just determinant of L minus kappa E. Then we have M minus kappa F. Then we have M minus kappa F, and then finally N minus kappa G. This is equal to 0, right? And the principal vectors corresponding to the principal curvature kappa are the tangent vectors T vector is equal to sigma U vector plus eta sigma vector, such that, and of course we are just relying on the same expression here. So kappa E M minus kappa F and minus kappa F. This would be a this is of course a matrix, but I prefer to use square brackets, and minus kappa G. Then we have zeta and eta. This is equal to 0, 0. So we solve this to obtain our what to say the principal vectors, right? Okay. So what I will do now is that what we'll do is now we'll move on to the 5th module today, and we'll not so the idea is that we will start with a bit on the Gaussian, I mean all that theorem acronym, right? And we would also do some talk a bit about its application in mechanics. And due to the shortage of time for this course, although we tried our best, but it still remains that we were not been able to cover it quite depth. I believe it's not very easy to to try to finish or to cover all aspects of differential geometry in such a short time, right? So so what we'll do now is that so we begin with module 5. Okay, so in this session, yeah, so we had not been able to talk about Gaussian. We did not have sufficient time to talk about many of the topics that we had planned due to the shortage of time, and it's of course not very um, it's not possible to cover all aspects of differential geometry in such a short time. So today we will, of course, I had discussed about the Christoffel symbols in the module 4 itself, right? And so we'll just list down certain important aspects of Gauss theorem egregium, and I'll just list down the Gauss-Maynard equations, right? And in mechanics, we'll talk about Rudd theories and a little bit on the ribbon theories. I'll just provide the formulation. And shell theory, it won't be possible to talk about in the short. Try to address it in a future course if time permits. Right? Okay. So today, let's talk. Begin discussion in the module 5. We begin our discussion with Gauss uh, theorema egregium. And this happens to be one of Gauss' most important discoveries. This one of the Gauss' most important discoveries about surfaces. So the idea is that the Gaussian curvature is unchanged when the surface surface bent without stretching. So that's the reason Gauss called this result as egregium, in a sense that in Latin it it implies remarkable, right? So that, and the thing is that it's still called the remarkable theorem, in the sense that it tries to address some very important aspect of a surface. That, say, if we just bend, twist a surface, doesn't matter unless it's not stretched. The Gaussian curvature always remains constant, right? So that's the reason Gaussian curvature is also sometimes called as the intrinsic curvature. There's something which is intrinsic to the surface itself, and no matter and it will be met. And a proper saying goes that it can Gaussian curvature is the only curvature which can even be measured by any, say, bug which is lying in a surface, right? So if a bug is just is traveling on the surface, it can still measure Gaussian curvature. So that's the thing about Gaussian curvature. However, the mean curvature is called as extrinsic curvature. And we know very well that if you can just change the direction of normal vector, just the sign of the normal vector, the mean curvature also changes. However, Gaussian curvature still remains as it is, right? So it's invariant to such changes in the normal vector. So, and here Gaussian, the theorem of egregium, it tries to relate the first and second fundamental forms of a surface. And that is a very important thing that we are still able to connect, because what we know is that the first curvature, the first form tells us about the measure of length on a surface, right? Measure of length of a curve on a surface, or otherwise, it gives us a measure of a length of any curve, and it has nothing to do with how much the curvature, how much the curve curves, right? Likewise, but the second fundamental form here has a different connotation altogether. It gives us how much how much the curve on a surface curves, or how much a surface curves, right? So essentially, it denotes some aspect of some sort of a curvature, right? So that is the distinction between the first and second fundamental forms. However, for this one, so theorem agreement relates both of them. Okay, so now let me start with the Gauss and so what we call as the Gauss and Codazzi minority equations. So the idea goes as we'll start with a proposition. Uh, so let E du squared plus 2f du dv plus z dv squared and L du squared plus 2m du dv plus n dv squared be the first and second fundamental forms. Surface patch. Sigma vector UV and define the Christoffel symbols as we had done in the previous sessions. Then, and this proposition actually represents what we call as the Codazzi minority equations. Sorry. So then LV minus MU is equal to L. Christoffel symbol is sigma gamma 1 1 2 plus M gamma 1 2 2 minus gamma 1 1 1 minus N gamma 2 1 1. And then we have MV minus NU is equal to L gamma 2 2 1 plus M gamma 2 2 2 minus gamma 1 2 1 plus N gamma 1 2 2, right? So this was the Gauss, the Codazzi Maidani equations. And then we also have a set of, and this equations, we can clearly say that the relation is between the Gauss curve, the first fundamental form and also second fundamental. But the second fundamental, of course, is obvious LMN, but first fundamental form is used to compute the Christoffel symbols, right? So then we'll have another proposition. And these are called as Gauss equations. Right? And here it states that if K is the Gaussian curvature of the surface patch, sigma UV, and of course, in the preceding proposition, Then what we have is we can explicitly see first and second fundamental forms. Uh, Again, second fundamental form is of course contained in these principal curvatures. Then we have sigma 1 as gamma 211 differentiated with respect to v minus gamma 212 u plus gamma 11 gamma 212 plus gamma 112 gamma 222 minus gamma 121 gamma 112 gamma 12 squared. And likewise fk is equal to gamma 121 minus gamma 111. This is respect to v plus gamma 122 gamma 121 minus gamma 2 gamma 211 gamma 221. Okay, and then we also have one more expression for fk, and this is 212 v minus 222 u plus gamma 121 gamma 212 minus 221 gamma 112. Okay, and gk is equal to gamma 221 gamma 112 plus, okay, uh, gamma 122 gamma 112 gamma 112 minus 212 122. These are the Gauss equations, right? And now you directly jump to the Gauss remarkable theorem, and I'll just be giving the expression for uh, Gaussian curvature, right? So it is what we have is the Gauss remarkable theorem. Right, and the theorem is also called as Gauss theorem egregium. Right? It states that the Gaussian curvature of a surface is preserved by local isometries. And as we recall, isometries are any such maps which preserve the lengths of a curve, right? So that is what, so which means that Gaussian curvature of a surface is always preserved by local isometries. So if the deformation takes place such that all the local symmetries are preserved, uh, if all the measures or the lengths of curves on a surface are preserved, then the Gauss curvature is also like preserved by such transformations. So ideally, I mean, commonly speaking, it implies that if S1 and S2 are two surfaces, and F from S1 to S2 is a local isometry then for any point P vector is an element of S1, the Gaussian curvature of S1 at P vector is equal to that of S2 at FP vector, right? And this theorem, right? So this theorem or the theorem, right, is sometimes expressed by saying that the Gaussian curvature is an intrinsic property of a surface. And so note the keyword here is intrinsic, for it implies that the Gaussian curvature could be measured by a big bug, but by just, of course, a bug living in the surface. Right? So corollary follows from here that so the corollary states that the Gaussian curvature is given by K is equal to minus half EVV plus FUV minus half GUU. Then we have half EU, right? And then FU minus half EV. And then we have FV minus half GU and half GV, then E, then F, then F and G. Determinant of this minus determinant of 0, half EV, half GU, half EV, EF, FG, and then half of G. So this is the corollary here. It's some space divided by Eg minus f squared and whole square. And oftentimes we may not require the complete expression of this. Okay? We would not require the complete expression of this the Gaussian curvature. We would always have certain special cases that we always deal with, right? So we'll follow it up with a few corollary. The first case is, say, number one, if f is 0, then we have, so f0 itself implies that many of the terms will go away. So I'll just give the final expression of what the Gaussian curvature it looks like. Minus 1 by 2 root over Eg. And then partial of partial u of Gu divided by root over Eg plus partial of partial v Ev of this Gu root over Eg. Right? So this is what we have. And now we have a special case of if E1 is 1 and f is equal to 0. Then we have k is equal to minus 1 by. So putting E1 is equal to 1, so this term anyway goes away, right? So this terms goes away. So we have Gu by, and then we have just root over with 2 root over G, and then partial of partial U, and G root over 12 by 2. Essentially, this is the case here, right? This EV. This may be simplified as 1 over root over G partial square root G by. Okay. And for the proofs and all, I believe we have all that. Let's do one example before we end today's session. So example, let's consider again the surface of revolution. And it goes as sigma vector u comma v is equal to f of u cosine v, f of u sine v, and g of u, right? And of course, all those implies f is greater than 0 and all the rest of the conditions. So say f dot square plus v dot square is equal to 1 and all. And we found that E is equal to sigma u dot sigma u, and sigma u is nothing but sigma u is equal to, what is it? F dot sine v, f dot sine v, g dot sigma v is equal to minus f sine v and f cosine v and 0. So sigma u dot sigma u is equal to f dot square plus and all that. So f dot square plus z dot square, right, is equal to 1. And f is equal to sigma u dot sigma v. And this gives us minus ff dot sine v cosine v plus ff dot of sine v cosine. So this is 0. And so g is equal to sigma v dot, sorry, sigma v dot sigma v. And this gives us f squared. So you can clearly see that E is equal to 1, this check, and F is equal to this check. So we have this condition, E1 is equal to F is equal to 0. So therefore, Gaussian curvature in this case is minus 1 by root over F squared. And then we have partial squared by partial U squared of root over G, which is F. So we have minus 1 by F and partial square U partial square, and this is simply F double dot by U by F. And where P, as we know, and this we had obtained in a previous session, this expression for the Gaussian curvature. So with this, we end today's session, or this session here, and the next session, next lecture would be on Redd theories, and which is going to be the last one. And yeah, with that, I'll just close for here the next session for this.